Today, I'm going to talk about the pH electrode and how it works. Let's go ahead and identify the parts. Every pH electrode has glass ball that comes in contact with the solution. There is a wire that conducts electricity and is on the inside of the electrode, which is directly connected to an internal microchip. Surrounding this wire is an electrical conductive solution called an electrolyte solution. The solution is normally a KCl potassium chloride solution of a concentration near 3.5 molar. The KCl solution can be a gel or a liquid depending on its designed use. This KCl solution leaks out of the glass bulb through a junction at a specific rate. Example, cloth junction equals 14 microliter per hour. There are three basic types of junctions to allow for the leaking of the electrolyte KCl solution into your testing solution. Ceramic junction, normally used in large-size particulate solutions with low concentration, for example, city water. Cloth junction, normally used in medium to large-size particulate with high concentrated solutions, for example, plant nutrient solutions. Open junction, normally used in small to large-size particulate with high concentration solution, for example, wine. On the bottom layer of the glass bulb, you have a gel layer that must be hydrated for proper use. You will have your glass bulb submerged in a testing or storage solution that will submerge the junction. For this example, we are going to show you H+, hydrogen ions, HOH, water molecule, OH, hydroxide ion. pH stands for potential hydrogen ions. When measuring the pH of a solution, you are measuring the number of hydrogen ions in that solution. A large number will create an acid solution, and a low number will represent a base solution. Now, we are going to show how all these parts work together to get you a pH reading in a few seconds. Submerge your pH electrode so that the junction is in contact with your solution. The electrolyte will begin to leak out of the junction at 14 microliters per hour. A millivolt electrical charge is supplied to the wire from the meter's battery. The millivolt charge will flow down the wire through the glass bulb, electrifying the hydrated gel layer. The hydrogen ions in your solution will migrate toward and attach themselves to the hydrated gel layer. The number of hydrogen ions inside of the glass bulb versus the number of hydrogen ions attached to the gel layer will ultimately decide your solution's pH value. This is dependent on the millivolt charge transmitted through the hydrogen ions from your solution. If more hydrogen ions are attached to the gel layer than are inside the glass bulb, this will create a low pH value called an acid. If less hydrogen ions are attached to the gel layer than are inside the glass bulb, this will create a high pH value called a base. Equal hydrogen ions on both sides of the gel layer and glass bulb will create a neutral pH value. This is created by a millivolt charge close to zero. Based on the number of hydrogen ions in this example, we would expect about an 8 millivolt charge. This 8 millivolt charge needs to re-enter the pH electrode to be transmitted to the microchip so the nearest equation can provide a pH value. The junction type leaking 3.5 molar KCl, a high salt electrical conductive solution, into your example, will now serve as a liquid wire to transmit the 8 millivolt signal through the liquid wire, junction, metal wire, and into the microchip so the nearest equation can generate a pH value. This concludes how your pH value is created with a millivolt charged pH electrode. Thank you for watching an educational copyrighted video from pH Professor.